to review a little bit, today we're going to be talking about freezing water.
Oh my
You,
gosh.
I know,
Oh
it
my
seems
gosh.
it seems at first like this is just a really, really basic, well, we know how to freeze water. You put water in the freezer and it, cools down and it now becomes ice. But we've got a little bit of review before that because we're going to be talking about freezing water in here, and we don't have a freezer in here, okay? Does ice melt?
Yeah.
Yes, it does. Okay, what is the melting point of ice? What is it? 0 degrees what? 0 degrees Celsius. If we're talking in terms of Fahrenheit, which in the scientific world, we typically don't use, we want to use Celsius, right? But when we look on our thermometers, usually we talk about it being 32 degrees Fahrenheit, right? For today, we're gonna talk about it in terms of Celsius because we're scientists right now. Okay? So yes, we know that ice does melt. Does water freeze?
Yeah.
Yeah, what could we use to freeze a volume of water?
A cooler.
That would do it, right? A freezer. Anybody have a freezer at home? Uh-huh.
No.
Well, we don't have a freezer in here though. How else could we freeze a small volume of water without using a freezer?
Like get a separate cup, like okay, so like a bag and fill it up with a little bit of water and then surround it with ice.
Okay, I've got something kind of like that. We'll talk about this in a little bit. I've got a vial of water in the middle, and then there's ice around it, so something kind of like this. Okay, that's just a thought. We'll talk about that more. What else?
We could open all the windows and lower the temperature really cold.
Okay, open the windows, make the air temperature super cold. How cold would it have to be in here?
32, well,
32.
to be ensured that it would freeze up 30 degrees, but
Okay.
it could be 32.
Okay, what else could it be? Well, that's not good.
If it were 33 degrees, would it melt? I mean, would it not freeze for 33 degrees?
How else would we make some water freeze? Take the water outside when it's below freezing, right? Anything else? I'm kind of surprised you didn't say this, Noah, because you mentioned it before. When I was crushing this ice. A different kind of ice that's a little bit more expensive, harder to find. Dry ice, right?
Seriously, man.
So there's a couple different things we could do to take a small amount of water and make it freeze. Right? We're going to attempt to do that here. Before we do, I want to show you this stuff that I've got up here. Got more ice for us later. I'm just going to move this over because hopefully then our video picks it up. Kind of.
EO.
There we go. Okay, so what I've got going on here, on the inside is a little vial like we had with the white powders that we were using. That's in the middle of the cup. The outside of that vial is surrounded by ice. I tried to crush it as much as possible, but I've still got some big chunks in there, which is, I'm hoping that doesn't mess this up. Can you come up here, please?
Okay.
I think these thermometers they've been sitting in here a little while now. Can you tell me the temperature of the water and the temperature of the ice?
The temperature of the water is about 6 degrees.
All right, we're going to keep an eye on the water then. We're hoping it gets a little cooler. Temperature of the ice?
0 degrees.
Okay, so ice is 0 degrees. Thank you. You can take a seat. So with our current experiment, ice is 0 degrees. The water, you said 6 degrees, huh? What are you talking about? It's down to like 2 degrees now. And I think in a little bit, I'll just let you know, in a little bit, the water should be about 0 degrees too. Okay, it might just not have sat in there long enough. Okay, but that's really what we're starting with. The water in the middle, 0 degrees. The ice surrounding it, 0 degrees. Okay, so now, if that's the case, water freezes at 0 degrees. We already said that, right? Is that water frozen? And I know it hasn't gotten there yet, but once it gets to 0 degrees, is it going to freeze? Yeah.
No.
You don't think so?
Because it
Are we
has
at
to
0 degrees yet? Oh, we're still just hovering a little bit above it, I think. Who thinks it's going to freeze when it gets down to 0? Raise your hand. Who thinks it will stay as water when it gets to 0? Okay, most of you are saying it stays as water. Doesn't ice melt at 0 degrees? So is the ice going to melt? Why might the ice melt? That's a little. I think that one's a little bit easier in this case. If we left this sit here and we came back in the afternoon, is the ice going to be melted?
Yes,
A little bit. Why?
the room temperature.
Yeah, the room temperature is going to melt that ice. And actually, if I put the lid, if I put the lid back on the water, then the room temperature wouldn't affect it either, right? Or it'd take a lot longer to affect it. Okay. Will this water freeze in a little bit? Most of you said no. Okay, so I want you to talk about that a little bit before we come back to this and before we test something out with the water. Okay. So I want you to partner up with somebody. We're going to take maybe 3 minutes for you to discuss these questions and come up with what you think the answer is going to be. Do the particles in the ice or the particles in the water have more average kinetic energy? Now we're going with the thought that pretty soon they're both going to be at 0 degrees Celsius. Okay, which one's got more kinetic energy? Number 2, if the particles of the ice and the water have the same amount of average kinetic energy, which one will transfer energy, or which way will energy transfer? Excuse me. What do we call that condition? And then what do we have to do to freeze this water? Because that's really what we're going to be doing over the next couple days. What can we do to transfer energy away from the water in the vial so that it will freeze? Okay? Go ahead and pair up with somebody next to you. Talk through those 5 questions. Watching the video, you can talk about it with somebody at home or just think about those on your own.
Or the particles in the water have more
Particles in the ice or particles in the
It will
water have
transfer
more
both
average
ways.
kinetic
I
energy.
will,
The particles of ice and water
Yeah.
Have more average kinetic energy.
What do we call this condition?
I'd assume the water.
Most people are going to assume the water, and that's going to be a assumption.
Kinetic energy not necessarily mean that temperature.
It's not. It's based on temperature, it's not based on phase. So really, we're both okay, so that's the case.
We have to go to
Really, number 2 says if particles of ice and water have the same amount, which way will the energy transfer? Usually we don't have to, but now there's
There's gonna be some fancy equilibrium.
What can we do to transfer energy away from the water in the vial?
Different source.
We can turn the thermostat down.
I am so.
Okay, you got 10 more seconds, try to finish up your discussion.
And it will, the ice will freeze, the ice will melt.
Okay, goodbye.
It has to be consistent.
All right, number 1. This is the question. If I was going to guess which one we would get incorrect, and there is a correct answer to this, this would be my guess. Do the particles in the ice or the particles in the water have more average kinetic energy?
The water.
How many of you said water?
Oh,
Water is not the correct answer. Neither is ice. It's kind of a trick question.
oh.
If they're both at 0 degrees, they both have the same amount of kinetic energy. And I think we probably are thinking about this in terms of phases, like, well, it's moving around more, the particles are moving around more quickly, right? Ice is solid, so they're mainly just vibrating. But remember, you got these different types of kinetic energy. There's like rotational, there's vibrating kinetic energy. What else am I missing? Translational, we haven't gotten into that, but really the amount of kinetic energy is based on temperature. It's not necessarily based on phases, okay? And that's what number 2 says. If the particles of ice and water have the same amount of average kinetic energy, they do, then which way would energy transfer? Because doesn't energy always flow from hot to cold? But in this case, we've got 2 that have the same amount of kinetic energy, right? Instead of flowing from a higher amount to a lesser amount, we don't have that. So what do we get?
We get equilibrium, they go back.
Yeah, they're going back and forth, right? There's still all these little collisions of particles. And you answered number 3 as well. What do we call that condition? That's equilibrium. When you got the same amount of kinetic energy and you got this transfer of energy back and forth between the 2 things. Okay, so if that's the case, what do we have to do to freeze this water that's in the middle there? Because right now it's in an equilibrium state. They have the same amount of kinetic energy.
We have to make it colder,
Make what colder?
either one.
Okay. How? Matthew.
Okay, see, this is why I think the ice will melt and the water won't freeze. It's because of the surrounding air, because it's above freezing temperature, meaning that it will always be heated up by the surrounding air and cannot be freezed because it's already in equilibrium.
We have to change something though so it's not in equilibrium, right? If
Yeah,
it
you
stays
have
in
to-
equilibrium.
You have to put it into a colder environment so that it can freeze.
Okay. What does it mean to freeze? If I got water right now, what do I have to do to the water so that it loses? I don't want to give it away here. Based on what we just talked about here with particles and kinetic energy, what are we trying to do to freeze something?
Take away its kinetic energy.
Yeah, we want it to transfer kinetic energy out. In other words, we need to have the surrounding area be colder so that it flows from the warmer, more high-level kinetic energy out to the surrounding area. Okay, so you get something kind of like this, right? We've looked at an image like this before. This is basically a larger version of what we've got set up now. If we can change the ice to be cooler than 0 degrees, right? If this is, right now, we've got this at 0 degrees. If we can make this like -3 degrees, isn't energy going to transfer out like that? And that'll drop the temperature here, and then it'll freeze. So how in the world do we get it to do that? How do you just make ice colder? Ideas?
More ice. Ice, baby.
More ice to make ice colder. Not if it's at the same temperature. How can you freeze water in a classroom? In other words, how can we make that ice colder so that we don't have that equilibrium, but we actually have energy flowing out? What do you think?
To have a consistent flow of cold energy towards the ice so it gets colder.
A flow of, say that again?
Like a consistent flow of energy. I don't know.
Okay. Matthew.
You either need to have more. You have to make it colder in order for it to transfer more.
How am I going to make ice colder?
By having either more of it or
More ice isn't going to make colder ice, right? If I would just dump more of this ice in that cup, it doesn't make the ice colder, it just makes more ice particles.
it's going to be more of a energy for the water.
I think we've got enough ice in there though, because there's such a small amount of water. I think I see what you're saying, like, right? You got a cup of soda or something like that, you put 1 chunk of ice in there, the ice melts quickly because there's so much energy transferring to the ice. And so let's add some more ice. But I think we've already got plenty of ice. We got much more than the actual small amount of liquid. What do you think?
Me?
Yeah.
We just use the AC.
Yeah, we're not gonna do anything with the air. We're gonna just change the ice. Here's what we're gonna do. Remember these different types of white substances that we've used in a multitude of different experiments?
Yeah.
One of these things added to ice makes the temperature of ice cool down. Okay?
Oh my gosh.
So we're gonna first test this out. And we're gonna see which one will cool the ice down. So like mixing in chalk with ice or mixing in road salt with ice. And we're gonna see which one of those drops the temperature of the ice, because then when the temperature of the ice out here drops, then we should see that energy transfer, which is gonna cool down the water as well.
Can I make a educated guess on which one it would be?
Sure, what do you think?
Salt.
Salt?
Yeah.
Hold on, let me show you the list.
Salt would-
Water.
Salt
Not salt, not water.
would lower the freezing temperature, making it melt.
Any other guesses?
But what was that ice salt challenge that happened like 5 years ago? Where people put salt on ice and then put it on their arm and then try not to bear the pain?
I don't remember that.
Well, I mean,
There's been like a stupid challenge every year, and let's do something dumb and videotape it. Tide Pod. Oh my goodness. Let's do something super dangerous and really gross. Make sure we capture it on video to prove to the rest of the world how dumb we can be. Yeah. Tide Pod challenge. Any other guesses though? Salt is one of them. What do you think?
Since there are 3 different types of salt, I'm guessing it's the Epsom salt or the table salt.
I just have 3 different kinds because that's what we use.
So road salt melts it, that's what they put in the road.
Every
don't
salt
Okay.
melts ice.
You don't want it to melt.
Half.
Okay, so here's what we're gonna do. You've been given the instructions with this. I think we should be able to do mainly pairs. Some of you might have to do a group of 3. In your tray, you've got a cup like this. I think they've all got that line on it. Doesn't have to be perfect, but pretty close to that line, so halfway up or maybe slightly more than that. You've got a stir stick. You've got, depending on which tray you grab, like this one's sugar, they're laid out so that each of these is in a different tray. So we're basically going to be doing a bunch of different experiments, but we're going to do it the same way. You've got a thermometer, and then you've got a scoop to scoop out whatever white powder you're using. The only thing that's not in there is the ice itself. So I've got this bag of what is supposed to be crushed ice, and I'm going to crush it a little bit more. So every group will come up and fill this up with ice to about that amount. And then we're going to place 2 milliliters of whatever white substance is in there. Excuse me, I take that back. Let's take a look at the sheet, make sure I'm not missing anything on the procedure. But we're going to fill up the cup with ice. Then we're going to measure the temperature itself, okay, which should be what? Should be 0 degrees. Then we're going to take the white substance and the spoons. We're going to try to do this all together, okay, so that we can time it. Why do you think we might do that? Why not have your group start, now you guys start, and whatever else? Yeah.
So we can get the starting time accurate and so that, we can see which one of the substance actually makes it cool down.
Yeah, and because you said to get the starting time accurate, really that's controlling a variable, right? There's different things that we could do differently in an experiment. We want everything to be as controlled and the same as possible. Time is one of those things. Any other variables that you can think of that we need to make sure we can control as we're doing this? Matthew?
Air temperature.
Okay, and that's gonna be the same automatically, right, because we're in the same room? But I wouldn't say, oh, you guys do it in here, why don't you guys do the experiment outside, right, because then that varies, we don't want it to vary. Anything else? If your group has sugar and you dump in like 4 spoonfuls of sugar and they've got road salt and she dumps one scoop of road salt in, is that gonna give us accurate results? No, so the amount of substance that we put in, and same thing, the amount of ice, right? That's why we got that little line. I said at least get it pretty close, as close as we can. What else am I missing? Oh, same kind of cup setup. right? We don't wanna have, oh, you go do it in here, we grab a big gallon. No, do it the same way. If you think of others, let me know. Okay, so anyway, once we're all ready, we're gonna take 2 milliliters and, 2 milliliter scoops, so a total of 4 milliliters of whatever substance you've got. You're gonna stir it in, and then we're gonna put the timer on. And actually, we can probably do, I'm gonna give you a separate cup, because it does say we're gonna do it in 2 separate. One will have 2 milliliters, so just 1 scoop. A different cup, I gotta get it out and give it to you, will have 4 milliliters. So really, we're gonna test each one of these in 2 separate ways, or with 2 different amounts. Does that make sense? Once we're done with all that, we're gonna make sure we record the temperature at the end, and we're gonna list this all out as a class. So whichever group gets calcium carbonate, just number of scoops, 2 and 4. Am I reading that wrong? 2 scoops, which would be 4 milliliters, or 4 scoops, which would be 8 milliliters. We're taking the initial temperature and the final temperature, and we're gonna see how much did it actually change. Did it cool it down? Maybe it heated it up, but that way we can see which one of these cools ice down the best. Are we okay with that? All right. Anything else I wanted to share with you? Well, I'll give this to you now. This is really going to be the sheet that we use to track this. Okay, so each one of you has an individual sheet, and then we're going to put our results up on the board. The downside is we're running out of time, and I don't think we're going to be able to do this entire experiment and get it cleaned up on time. So let's save it for tomorrow, which actually isn't that bad because that gives me a chance to crush the ice a little bit better. Sound good? All right, we will do that first thing tomorrow.